Alright, and in this video we're going to go through an example. We love talking about ice cream cones, don't we? Seems like we always have an ice cream cone problem in our work. But here we go. Alright, so we have an ice cream cone and you can see it all. Alright, so take a minute to pause the video and read through it, think through it, and attempt this on your own. We do want to set this up with 3 different representations, so Cartesian, cylindrical, and spherical. See if you can do that on your own before resuming the video. Alright. So, we just need to set this stuff up. So, Cartesian, we're going to have a triple integral, and I'm going to space them out a little bit. And then we have a function, and since we're finding the volume, right, then it's just 1, and then whatever the order we choose. Okay? The order that I'm going to choose for Cartesian is dz, dy, dx. If you have a different order, hey, great, go for it. Alright? So z, as I think about z, it's going to extend from the lower function to the upper function. This one is actually kind of easy. So the lower function is the cone, and that's just the square root of x squared plus y squared. And then the upper function is the hemisphere. And when you solve for z and do the upper part, you end up with square root of 1 minus x squared minus y squared. Alright. So that's fine. Well, next I need to figure out, okay, well, what about the function y? And y needs to be in terms of x because these are elementary regions. Well, the trick here is going to be I need to figure out that point of intersection, right? If I end up substituting in this function in for z here and solving, what I end up with is 2x squared plus 2y squared is equal to 1, and then divide by 2, etc., whatever, you just end up with x squared plus y squared is equal to 1/2. Okay, so then if I solve, and that would find this boundary, okay, where they meet, and so then that would be a nice way to restrict my function. I would go from negative square root of 1/2 minus x squared, and then, at least in the xy plane, that would be the furthest I would have to go out to, and then, let's see, the positive version as well. Okay, and then, certainly in this scenario, if y was 0, x would have to extend from minus 1 over root 2 to positive 1 over root 2. Okay, so that's one order for the Cartesian representation here. Okay, if we change to cylindrical, I think our lives get a lot easier. So again, if I think about this, okay, so I would be hard pressed to do this thing in Cartesian myself. I would much rather do it in cylindrical or maybe even spherical. But in cylindrical, remember you need that Jacobian r, and then we have, I'm going to do dz, dr, d theta. Okay, d theta is actually super easy, 0 to 2 pi. Okay, theta goes in that direction, and then r, as we found out above here, right? R is going to go from 0 to 1 over root 2. Okay, and then in terms of z, this is where it could be a little bit interesting. Z, well, when we think about z, we still need to extend z from the lower to the upper, and the upper is just, or the lower is just r, and then the upper is just going to be square root of 1 minus r squared. Okay, well that was easy enough. That was much easier and much nicer to work with. And then in spherical, again, triple integral, and then 1 times the expansion factor of sine, or rho squared sine phi, and then I'm going to use the order d rho, d phi, d theta. Okay, and again, theta is going to go from excuse me, 0 to 2 pi. Okay, phi is going to go from 0 to pi over 4. Okay, that's to give you your sides of your cone, and then rho is going to go from 0 to 1. Okay, so again, just a quick example of the of doing this in different coordinate systems, and then I guess thinking about which one you might want to use if it isn't specified. Alright, so in the next video we'll do one more example and then we'll be done.